So here is the crux of the matter. What is electricity? Electricity is the result of a flow of moving charges. Those charges could be electrons flowing through a wire. They could be ions in a solution, that is, charged particles in a solution. You can even have static electrical charge that'll be discharged. But essentially, in the capacity of electrochemistry, it's going to be electrons moving from one atom to another atom or one ion to another ion. So electrical potential is, you can think of this as electrical pressure. We measure this in a unit called voltage. Or volts. We can also characterize it as electromotive force, and it's simply the force that pushes charges to make a current. So here's an analogy that gets used a lot with respect to voltage. So voltage is kind of like the pressure. Let's say we have water in a vertical pipe, and the water in that vertical pipe is creating a pressure that down here at the bottom by virtue of the gravitational pull on the mass of water in that pipe. And so we could think of that pressure as potential. Okay, so that pressure is potential energy, like voltage is potential energy. Now, if we open up the spigot and the water begins to flow out of that spigot, we can think of that as the current or flow of electrons. So the water flowing out of the spigot is current, and current we measure in a unit called amps. So amps or amperes are the unit for the flow of current through a system. So voltage would be the pressure in our little analogy here in the water pipe, and the flow of water out once you open up the spigot would be the current in our analogy of water to electricity. Okay, so current measured in amperes, and it is the flow of charges. All right, let's take a look. What if we could make the electron transfer in a redox reaction occur through a wire? We already talked about having the electrons being transferred directly from one atom to another atom or ion, and that is a redox reaction. But what if we could separate the metals or the species, and over here on this side, we're going to have a zinc, what we call an electrode, and this is where oxidation is going to take place. So this will be our oxidation half reaction. You're already familiar, that's the loss of electrons. The zinc is going to give up electrons, let them go. Those electrons are going to flow from the zinc electrode through either a voltmeter, it could be an electric light bulb, it could be some kind of a motor, a machine, but essentially the electrons are going to flow through that machine. They're going to come down the wire on the other side, and they're going to go into, and this is a specific type of electrode. It's called the standard hydrogen electrode, or SHE, standard hydrogen electrode. And it's how we measure the cell potential, the reduction potential of any particular species. But in any case, we're blowing hydrogen in through this chamber here. We've got a 1 molar concentration of acid that's in this container, and the electrons come down and they get added to the hydrogen ion in this particular cell, and the hydrogen ion gets reduced to hydrogen gas. You can see that reaction right here. Remember, in a reduction half reaction, the electrons are on the reactant side, and so 2 hydrogen ions are being reduced to hydrogen gas on this side. Now, we have some terms that we need to apply to where oxidation takes place and where reduction takes place. And we'll just kind of start you off. We're going to go over this a lot, but oxidation takes place at the anode. Anode, oxidation. Oxidation, anode. They both start with vowels. Oxidation starts with O, anode starts with A. Electrons flow from the anode to the cathode. And the cathode is where reduction takes place. So cathode, reduction. They both start with consonants. R for reduction, C for cathode. Cathode reduction. So electrons always flow in what we call a voltaic cell from anode to cathode. All right. Now we're going to talk about something called the salt bridge. If you have this continuous loss of electrons from the anode, oxidation, you're going to build up positive charge in the anode compartment. So you need a way to balance that charge or your battery will stop, your voltaic cell will stop. And so anions in the salt bridge flow into the anode compartment. Again, anions start with A and anode starts with A. So anions in the salt bridge to the anode compartment. Over here in the cathode compartment, you're reducing positive charge, so you have to have a way to put back your positive charge. And so cations in the salt bridge will flow into the cathode compartment to restore a balance to charge. Okay? And you'll notice that for the oxidation half reaction, you can see it right here. This is where zinc is being oxidized. In an oxidation half reaction, again, the electrons are on the product side. And in a reduction half reaction, the electrons are on the reactant side. All right, let's keep going. All right, so here's what we call a voltaic cell. A voltaic cell is a spontaneous reaction where electrons spontaneously flow from the anode, which is negatively charged. They go through a wire to the cathode, which is positively charged. Anode, negative charge. Oxidation occurs at the anode. You can see it right here. The zinc is being oxidized. Electrons are on the product side. The electrons flow from the anode to the cathode, which is positively charged. The electrons are coming in here. They're reducing, in this case, they're reducing the copper 2 plus ion to copper metal. It collects over here on the copper cathode, the copper electrode, which is the cathode. All right, and this is the reduction half reaction. Once again, the electrons are on the reactant side of a reduction half reaction, and the oxidation state is getting lower. Over here, copper has a 0 oxidation state. On the reactant side, it has a +2 oxidation state. 0 is a lower oxidation state than 2+, which is how you know this is reduction. Where does reduction happen? It happens at the cathode. This is oxidation. And oxidation, the electrons are on the product side. Where does oxidation take place? At the anode. And in a voltaic cell, also known as a galvanic cell, electrons flow from anode to cathode. All right? And in the salt bridge, the anions flow into the anode compartment to balance charge because you're building up positive charge. So you're going to add some negative charge to neutralize the buildup of positive charge. Over here in the salt bridge, the cations go into the cathode compartment. Because you're losing positive charge, you need to restore positive charge by adding a cation to the cathode compartment. Okay? All right, and this is a spontaneous process. Key terms: anode, negative electrode, that's where oxidation takes place. That's the loss of electrons. Cathode, the positive electrode, that's where reduction takes place, gains electrons. The salt bridge contains mobile ions, inert ions that aren't going to do chemistry. They're just there to keep the charge balanced. Remember, anions, negatively charged anions, into the anode compartment. Cations, positively charged cations, into the cathode compartment. Anions to the anode, cations to the cathode. Remember that. Say it 5 times before you go to bed tonight. So here's a handy mnemonic. Anox, red cat. Anions to the oxidation half reaction, or anode oxidation. Reduction, cathode. So reduction, cathode, anode oxidation. All right. Cell potential is the electromotive force. That's the voltage. E of the cell is what is the cell potential. It's measured in volts, which we use the symbol capital V. So 1 volt is equal to 1 joule per coulomb. That may come into play a little bit later, but just remember, voltage is a measure of electrical potential. Voltmeter or potentiometer is what we use to measure voltage. Okay? All right, standard cell potential. Remember what the little 0 up here stands for. The little 0 up here stands for standard conditions. Standard conditions. Okay. Now, those are very specific. If it's a gas phase reaction, we're using 1 atmosphere of pressure. The temperature is 25 degrees Celsius, which is 298 Kelvin, and 1 molar solutions if it's an aqueous solution. Those are standard conditions, guys. That's what that little looks like a degree sign for E of the cell. That's under standard conditions. All right. So standard hydrogen electrode, that's what the SHE stands for, standard hydrogen electrode. This is the way we measure the standard reduction potential for different substances. We put over here, this is a container that holds hydrogen gas. Of course, it's at 1 atmosphere of pressure. It's hydrogen gas. We keep it at 1 atmosphere. Those are the standard conditions. What we're measuring is the tendency of this electrode to either oxidize or be reduced in reference to the standard hydrogen electrode. And so if the zinc chooses to oxidize in the presence of the standard hydrogen electrode, what we're going to wind up with is a positive oxidation potential, but a negative reduction potential. Let's look at this another way. If I take zinc 2 plus aqueous and I try to add 2 electrons to form zinc metal, since zinc metal has an oxidation potential that's a positive 0.76, zinc would have a reduction potential that is a negative 0.76 volts. All we do, if we reverse the oxidation to a reduction reaction, we change the sign. Or if we reverse the reduction reaction, we change the sign. So zinc metal going to zinc 2 plus, which is what is happening here, that has a 0.76 volt positive oxidation potential. Now, what you're going to find out is that potentials are written as reduction potentials, not oxidation potentials. But the standard hydrogen electrode is what we use to determine what wants to be oxidized, what wants to be reduced, and we assign a value in voltage which tells us what our potential is for that particular substance. All right? All right, standard reduction potentials. I'm going to kind of blow this up for a little bit so you can actually see it. And you might notice if we look at them, they're all written with electrons on the reactant side. That means these are all written as reduction potentials. You'll see the electrons are all on the reactant side. Now, all of these reduction potentials were determined by using the She electrode, the standard hydrogen electrode that we just looked at. And some of them want to be, so up here where you have positive values for all these species over here on the reactant side, those positive values means they have an energetic tendency to accept electrons, to be reduced. Now, if we go down to the bottom over here, you can see at the bottom you have a bunch of negative standard reduction potentials, and here's zinc included in that. Anything with a negative reduction potential would prefer, with respect to the standard hydrogen electrode, which we're depicting right here, because that's hydrogen right there. So that everything is referenced against the standard hydrogen electrode. These substances like nickel 2+, iron 2+, zinc 2+, even water, aluminum 3+.
I'm not quite sure how to help you with that.
Sodium and lithium, all of these have very negative standard reduction potentials, which means that, for instance, if I looked at nickel, nickel solid would much rather be oxidized to nickel 2+. Plus a couple of electrons. This, if the reduction potential is minus 20.28, then the standard oxidation potential would be a positive 0.28 volts for nickel 2+. Okay, I'm sorry, for nickel metal. Notice that I reversed the reaction where nickel metal is on the reactant side and it's being oxidized. You can tell that because the electrons are on the product side. And so the standard oxidation potential would be 0.28 volts. But they're all written as reduction potentials. So anytime you need to reverse one, you just change the sign. So for instance, if I took iron 3+ plus an electron to iron 2+, and I reverse that to iron 2+ being oxidized to iron 3+ plus one electron, instead of a positive 0.77 volts, I would say this has a negative 0.77 volts. This is its oxidation potential, which is negative, because its reduction potential is positive. Reverse the reaction, you reverse the sign. All right, and we're going to use that coming up here. Okay, let's talk about, let me get this down a little bit. Let's talk about agents, oxidizing agents, reducing agents. Here is the standard reduction potential table again. You'll notice that fluorine up here has a standard reduction potential of positive 2.87. What that tells you about fluorine gas, this guy right here, is that it really wants to be reduced more than any other element, which is not a big surprise. Fluorine gas is, or fluorine is, the most electronegative element on the periodic table. It would like to gain electrons to have neon's electron configuration, which is why it has a positive 2.87 volts standard reduction potential. So let's put it together with lithium, and let's see what kind of standard cell potential we have. All right, so the way we would do this is, you remember, you can't have a reduction without an oxidation. So that's going to be E of the cell under standard conditions is equal to the E of reduction plus the E of oxidation. I'll get to reducing agents and oxidizing agents in just a minute. Now, here's what this is saying. If I'm going to put these two reactions together, fluorine being reduced and lithium being oxidized, I have to reverse one of the reactions. And the one that I'm going to reverse is the one that has the lowest standard reduction potential. So the way we would write this reaction is we would say fluorine gas plus lithium metal. So that's a solid. This is a gas. Doesn't matter really. And then what we're going to get is we're going to get lithium plus 1 plus 2 fluoride anions over here, okay? Okay, so here we go. So the reason that fluorine is written as a reduction, it's gaining electrons to become fluoride ions, is because fluorine is the best oxidizing agent. Remember, oxidizing agents get reduced. And that's what's happening in fluorine. Fluorine has a huge reduction potential, a positive 2.87. Now, lithium plus 1, on the other hand, has a terrible reduction potential, lowest on the standard reduction potential table of minus 3.05 volts. That means that lithium ion would be a terrible oxidizing agent, but lithium metal would be a great reducing agent because I'm reversing the reaction. And so what we're going to have down here is lithium metal being oxidized to lithium plus 1 plus an electron. Lithium really wants to be oxidized, which makes lithium metal a great reducing agent. Okay, and so this is how we would calculate the cell potential. So if I add those two together to get the standard E of the cell, and you know it's standard because of that little 0 up there, that's going to be the E of reduction for fluorine, which is a positive 2.87 volts plus a positive 3.05 volts, which gives you a positive 5.92 volts. Now, that is a very positive standard cell potential, and in order to have a spontaneous process, a galvanic cell, a voltaic cell, you have to have a positive cell potential. So positive cell potential, E of the cell, means that this reaction is spontaneous. Okay, and the deal is fluorine, because it wants to be reduced, is a great oxidizing agent. Lithium metal, because it would love to be oxidized, is a great reducing agent. Remember, you take the most negative cell potential and you reverse it. All right? So let's put that together so you can simply use standard reduction potentials to determine the best oxidizing agents and the best reducing agent on a list. So as you go up the standard reduction potentials, let's see if I can straighten that line out. No, it didn't want to straighten out. But at any rate, as you go up the standard reduction potentials, you get the easiest to reduce, which means they're the best oxidizing agent. The more easily reduced, the higher the standard reduction potential, the better the oxidizing agent. And going on the other side, and that's down this side. Okay, so you've got to look at the right-hand side, the product side of the standard reduction potentials. As you go down the standard reduction potentials on this side, the right-hand side, you get to species that want to be oxidized. So the easier they are to oxidize, that is, the lower the standard reduction potential, the better reducing agent you have. Easiest to oxidize, has the lowest standard reduction potential. That makes the strongest reducing agent because it wants to give up electrons and cause something else to be reduced. All right. So which of the following, I'm going to kind of make this a little bit smaller. There you go. Which of the following halogens is the best oxidizing agent? The best oxidizing agent will be the most easily reduced. That's going to have the highest reduction potential. And so that is going to be fluorine, who wins at a positive 2.87. So let's go the other way and ask what would be the best reducing agent on this particular list. Well, the best reducing agent would be on this side. It has the lowest reduction potential, so we would flip that around. And so iodide on this particular list would be the best reducing agent, okay? But you would have to reverse this reaction. It's got a positive 0.53 reduction potential, which is a lower reduction potential than anything else, but you would have to reverse it to have your two iodide ions, and they would be giving up electrons, that is oxidized, which makes them good reducing agents, okay? Because this is going to be oxidized to I2. Okay, hopefully that wasn't confusing. Manipulating standard reduction potentials. If you reverse the reaction, just change the sign. If you multiply by the coefficients by a constant, do not change the standard E of the cell, because standard E of the cell is an intensive property. And you remember, intensive properties do not depend on the amount. Other intensive properties are things like density or color. They don't change with the amount, okay? So if you multiply by a constant, don't change the amount. Don't multiply your cell potential, okay? Doesn't change it, just makes it last longer. Thermoequilibrium and electrochemistry, the operation, multiply by coefficients by a constant, reverse a reaction, add to. This is just a summation of things you've already learned. And so I will leave you to remember that if you have a thermodynamic value, delta H, delta S, delta G, those are extensive properties. So if you multiply by a coefficient, then you multiply by the value by that coefficient. If it's an equilibrium constant, you simply raise the equilibrium constant to the power of whatever your multiplier is. And if it's a standard reduction potential, no effect, because standard reduction potential is an intensive property. If you reverse a reaction, if it's a thermodynamic value, you reverse the sign of the value. If it's an equilibrium constant, the reverse reaction, you just take the reciprocal, 1 over the K value, and you just reverse the sign of E of the cell. Adding two reactions, If it's thermodynamic, you just add their values. If it's an equilibrium constant, you multiply by their equilibrium constant, and then standard reduction potentials, you just add their values. All right, I'll show you how to do that. Finding cell potential. Add the half reactions to make the cell reaction. Multiply coefficients as necessary to make electrons cancel out. Do not multiply the cell potentials. Add potentials for the half reactions to get the cell potential. So here's our first problem. Okay, consider a galvanic cell based on this overall reaction. So we've got aluminum plus 3. It's going to be reduced. Magnesium is going to be oxidized. How can I tell that? Because on the product side it has +2, so I know it's going to be oxidized. And then aluminum's reduced. I know that because it's got 0 charge on the product side and a +3. So it's accepting electrons. All right, so if we're going to go ahead and balance this reaction, if you watch the videos on balancing redox reactions, this is the takeaway that you need. We need to get the number of electrons gained to equal the number of electrons lost. So if I have a differential number of electrons in my standard reduction potentials, all I need to do is I need to multiply the reduction of aluminum by 2. That's going to give me 6 electrons, and I need to multiply the oxidation of the magnesium. Well, it's still written as a reduction here, but we'll change that in a minute. And so I need to multiply it by 3. 3 times 2 is 6. So this will give us 6 electrons exchanged between aluminum and magnesium. So I'm just going to go up here, and I'm going to change this coefficient to 2, this coefficient to 3, this coefficient to 2, and this coefficient to 3. Aluminum is going from +3 to 0. That's reduction. Okay, and so that does tell us that this is our reduction reaction, although we don't need this to make that determination based on the cell potentials here. Magnesium is going from a 0 oxidation state to a +2. That is oxidation. That tells us that magnesium is the reducing agent. So this is our reducing agent. Why? Because it's being oxidized. And aluminum 3+ is our oxidizing agent because it's being reduced. But that's our balanced chemical reaction. Now we want to do the cell potential. So this will be our oxidation half. Now, if I didn't have this redox reaction up here, and I'm trying to figure out what the cell potential would be just given the E of the cell for the reduction potentials, I would notice that the -1.66 is a larger reduction potential than a -2.37 volts. Okay, so this is a smaller reduction potential. Take the smaller reduction potential and reverse it. So in calculating the E of the cell under standard conditions, this will be E of reduction plus E of oxidation. The E of reduction is a -1.66 volts. Plus, and remember, we're reversing the reaction. We're putting magnesium on the reactant side here. So we have to reverse the sign. This is now going to be a positive 2.37 volts. So it's a -1.66 plus 2.37. So that's a -1.66 plus 2.37, which gives me a positive 0.71. So this is a positive 0.71 volts. Now, you may not think that that is a really high cell potential. However, it is positive, and as long as the E of the cell is a positive value, that reaction under that set of conditions is spontaneous. That is, it occurs without outside intervention. You don't have to do anything to it. It just happens, and it produces 0.71 volts. Let's take a look at this one. A galvanic cell is based on the reaction. This is permanganate. We know that's going to be our oxidizing agent because it's got a +7 over here. And then we've got chlorate over here. That's a -2. That's a -6. None of this we have to do to figure out the cell potential, by the way. But at any rate, this has to add up to a -1. This is a -6. And then so this has to be a +5. So that's a +5. I'm just kind of doing some unnecessary stuff here. Oh, we're going to perchlorate. So it's just -2, 4 times the -2, -8. This has to add up to -1. So this is +7. So we're going up to +7, and then this is just a 2+. So manganese is going from, come on, give me a little bit more, +7 to +2, and that is a reduction. And of course, that makes permanganate the oxidizing agent because it got reduced. And then chlorate is going from a +5, that's a +5, to a +7, that's oxidation. And so since chlorate is being oxidized, that makes it since it's being oxidized, it makes it the reducing agent. Okay. Okay, so chlorate is the reducing agent, and permanganate is the oxidizing agent, none of which has anything to do with solving the problem. Give the balanced cell reaction and calculate E of the cell. All right. So let's go ahead and start over, and here's what you have to do. You can see that in one of the half reactions, a reduction of perchlorate, you have 2 electrons, and then over here in this other half reaction, you've got permanganate being reduced by 5 electrons. So we need to get the number of electrons lost and gained to be the same. And so it's pretty much a simple, you don't have any other multiple that you can use other than multiplying this entire reaction by 2 and this entire reaction by 5. Now keep in mind, cell potential, standard cell potential, is an intensive property, so that does not change the voltage at all. Intensive properties don't change with the amount. All right, the long and the short of this process is that you want to figure out the number of electrons that are being transferred. So on the test, if you're looking for the number of electrons transferred in this reaction, all you have to do is look for the least common multiple, since there's nothing you can multiply 2 by or 5 by other than each other to get the same number of electrons. This is going to be 10 electrons that are being exchanged. And we're just going to call that N for the number of electrons. Lowercase n is equal to the number of electrons transferred in a redox reaction. So transferred. Okay? All right. But we can go ahead and we can solve this particular problem when it did, just using the half reaction method. And so not surprisingly, since we're multiplying the permanganate side by 2, you're going to get a 2 in front of both manganese and permanganate. We're multiplying the chlorate perchlorate side by 5, and so that's going to be 5 and 5 here. The rest you had to determine using the full balancing, and I went ahead and did that. So we've got 6 hydrogens being transferred, and over here I have 3 waters being transferred. And that's after having canceled the 10 electrons, canceled a bunch of waters, canceled some hydrogen ions, but that's how I came up with the balanced chemical reaction. I just used the protocol that we practiced in the 2 videos I posted on balancing the reaction. However, let's get down to calculating the cell potential. Now, we know, looking at this reaction, that chlorate is going to be oxidized to perchlorate. And let's see if that fits. So it does. You can see that the highest reduction potential is going to be with the permanganate ion. And so this will be the reduction side of the reaction. And the lowest standard reduction potential is the 1.19. So we're going to reverse the sign and make that the oxidation half reaction. So in calculating E of the cell under standard conditions, that's E of the cell, we have E of reduction, which is going to be as written 1.51 volts plus, and we're reversing this you can see that the ClO3, the chlorate ion, is on the reactant side. That means it's being oxidized. All right, it's being oxidized from a +5 to a +7. So here we go. So we're going to reverse the sign, make this a minus 1.19 volts. Then just plug it in the calculator to figure out what our standard cell potential is. That's a positive 1.51 as written, and then plus a minus 1.19, which gives me a positive 0.32 volts. So we've got a positive 0.32 volts. The takeaway here is that because this is a positive cell potential, this reaction is spontaneous. That means it occurs without outside intervention. Okay, so you could use it for something like a battery. All right. So alternative with the textbook is to keep the signs the same and then just subtract. I would say take one method and stick with it, whether you use this method. I don't. I generally use the method that I just showed you, where whatever has the lowest reduction potential, I change the sign and then I add it to whatever has the highest reduction potential. All right, but you could do this. You could say, in this case, what did we have? We had, okay, I think I remember. We had over here a positive 1.51 volts, and we could subtract a 1.19 volts. We're going to get the same thing. We're going to get that positive 0.32 volts. So just using this method, I did not change the sign, but I did a subtraction instead of addition. Whichever way you choose. Choose a method, stick with it. I think this is a good place to end this one, and then we'll make a third and final video for electrochemistry, starting with line notation.